Jupiter is the fifth planet from the Sun, and the largest in the solar system. It is a gas giant with a mass nearly 2.5 times that of all the other planets in the solar system combined, and slightly less than 1,000th the mass of the Sun. Its diameter is 11 times that of Earth and a tenth that of the Sun. Jupiter orbits the Sun at a distance of 5.20 astronomical units, 778.5 gigameters, with an orbital period of 11.86 years. It is the third brightest natural object in the Earth's night sky, after the Moon and Venus, and has been observed since prehistoric times. Its name derives from that of Jupiter, the chief deity of ancient Roman religion. Jupiter is the biggest storm in the solar system, is the largest and most enduring storm in the solar system, a massive anticyclonic vortex that has raged for at least 150 to over 350 years. It is a reddish, oval-shaped storm, roughly 16,350 kilometers wide, about 1.3 times the diameter of Earth, with wind speeds reaching up to 680 kilometers per hour. When 17th century astronomers first turned their telescopes to Jupiter, they noted a conspicuous reddish spot on the giant planet. This great red spot is still present in Jupiter's atmosphere, more than 300 years later. It is now known that it is a vast storm, spinning like a cyclone. Unlike a low-pressure hurricane in the Caribbean Sea, however, the red spot rotates in a counterclockwise direction in the southern hemisphere, showing that it is a high-pressure system. Winds inside this Jovian storm reach speeds of about 270 miles per hour. The red spot is the largest known storm in the solar system. With a diameter of 15,400 miles, it is almost twice the size of the entire Earth, and 1/6 the diameter of Jupiter itself. The long lifetime of the red spot may be due to the fact that Jupiter is mainly a gaseous planet. It possibly has liquid layers, but lacks a solid surface, which would dissipate the storm's energy, much as happens when a hurricane makes landfall on the Earth. However, the red spot does change its shape, size, and color, sometimes dramatically. Such changes are demonstrated in high-resolution, wide-field and planetary cameras 1 and 2 images of Jupiter, obtained by NASA's Hubble Space Telescope, and presented here by the Hubble Heritage Project team. The mosaic presents a series of pictures of the red spot obtained by Hubble between 1992 and 1999. Astronomers study weather phenomena on other planets in order to gain a greater understanding of our own Earth's climate. Lacking a solid surface, Jupiter provides us with a laboratory experiment for observing weather phenomena under very different conditions than those prevailing on Earth. This knowledge can also be applied to places in the Earth's atmosphere that are over deep oceans, making them more similar to Jupiter's deep atmosphere. The Hubble images were originally collected by Amy Simon, Cornell University, Rita Beebe, NMSU, Heidi Hammel, Space Science Institute, MIT, and their collaborators, and have been prepared for presentation by the Hubble Heritage team. Jupiter's magnetic field is the strongest of all the planets. Generated by the liquid metallic hydrogen in its interior, the field is around 19,000 times stronger than Earth's, and extends several million kilometers towards the Sun, and almost all the way to Saturn in the direction away from the Sun. If it was visible to the naked eye from Earth, Jupiter's magnetic field would appear twice as large as the full Moon, despite being almost 1,700 times further away. The magnetic field at the tops of Jupiter's clouds is approximately 10 times stronger than Earth's, and its overall magnetosphere is 20,000 times more powerful, Laboratory for Atmospheric and Space Physics reports. Jupiter's internal magnetic field is generated by electrical currents in the planet's outer core, which is theorized to be composed of liquid metallic hydrogen. Volcanic eruptions on Jupiter's moon Io eject large amounts of sulfur dioxide gas into space, forming a large torus around the planet. Jupiter's magnetic field forces the torus to rotate with the same angular velocity and direction as the planet. The torus, in turn, loads the magnetic field with plasma, in the process stretching it into a pancake-like structure called a magnetodisk. In effect, Jupiter's magnetosphere is internally driven, shaped primarily by Io's plasma and its own rotation, rather than by the solar wind, as at Earth's magnetosphere. Jupiter has 95 moons that have been officially recognized by the International Astronomical Union. But the number doesn't capture the complexity of the Jovian system of moons, rings, and asteroids. The giant planet has thousands of small objects in its orbit. Scientists are getting so good at spotting tiny moons orbiting distant giant planets that the International Astronomical Union has decided the smallest will no longer be given mythological names unless they are of significant scientific interest. Jupiter's moons form a satellite system, colloquially referred to as the Jovian system. The most massive of the moons are the four Galilean moons, Io, Europa, Ganymede, and Callisto, all of which were independently discovered in 1610 by Galileo Galilei and Simon Marius, and were the first objects found to orbit a body that was neither Earth nor the Sun. Much more recently, beginning in 1892, dozens of far smaller Jovian moons have been detected and have received the names of lovers, or other sexual partners, or daughters of the Roman god Jupiter, or his Greek equivalent, Zeus. The Galilean moons are by far the largest and most massive objects to orbit Jupiter, with the remaining 93 known moons and the rings together comprising just 0.003% of the total orbiting mass. Ganymede is the largest moon of Jupiter, and the largest in our entire solar system, with a diameter of approximately 3,273 miles, 5,268 kilometers. It is even larger than the planet Mercury, and features a unique magnetic field, along with a likely subsurface ocean. Discovered by Galileo Galilei in 1610, it is one of the four Galilean moons. It is the only moon known to have its own magnetic field, which creates auroras around its poles. Ganymede takes roughly 7 days to orbit Jupiter. It is part of the four major, or Galilean, moons, which also include Io, Europa, and Callisto. It's easy to see why folks call Jupiter a failed star. Just look at it. This colossal gas giant, swirling with storms bigger than our entire planet, feels like it belongs in the stellar neighborhood. It's massive, it's gaseous, and it certainly commands attention. But here's the thing. Despite all its impressive qualities, Jupiter isn't, and never will be, a star. The reasons boil down to some fundamental cosmic rules, primarily about mass and the fiery process of nuclear fusion. Stars, you see, are defined by their ability to ignite and sustain nuclear fusion in their cores. This is where hydrogen atoms are squeezed together under immense pressure and heat, transforming into helium and releasing an incredible amount of energy as light and heat. Think of it as the ultimate cosmic engine. For this to happen, an object needs a critical amount of mass to generate that crushing gravitational force. And this is where Jupiter falls short. The minimum mass required for an object to kickstart sustained hydrogen fusion is a whopping 75 to 80 times Jupiter's current mass. Without reaching that threshold, the core simply can't generate enough pressure to overcome the natural repulsion between atomic nuclei. Jupiter, while enormous, about 318 times the mass of Earth, is only about 1/1047th the mass of our Sun. That's a vast difference in astronomical terms, placing it far, far below the stellar ignition point. Interestingly, if Jupiter had been about 80 times more massive, it could have indeed become a red dwarf, the smallest type of true star. Nature, it seems, came quite close to giving our solar system a second sun. Jupiter, as the solar system's largest planet, acts as a gravitational shield, protecting Earth by absorbing or deflecting many potential comets and asteroids. Its immense gravity can capture, destroy, or fling dangerous objects out of the solar system, acting as a cosmic vacuum cleaner. However, this effect is complex, as Jupiter can also steer some objects toward the inner solar system. How Jupiter protects Earth. Gravitational shielding. Jupiter's massive gravitational field, 318 times more massive than Earth, attracts and deflects comets and asteroids that might otherwise threaten inner planets. Cosmic vacuum. It acts as a target for comets and asteroids, such as the famous collision with comet Shoemaker-Levy 9 in 1994, which showed how Jupiter absorbs massive impacts. Orbital stability. Jupiter influences the asteroid belt, keeping many rocky bodies in place and preventing them from drifting into the inner solar system. Deflection. Jupiter can capture, destroy via tidal forces, or slingshot long-period objects out of the solar system. If Jupiter were to move from its current orbit into the inner solar system, it would almost certainly destroy Earth, or render it entirely uninhabitable. With a mass 318 times that of Earth, Jupiter's gravitational influence would be cataclysmic. 65 million years ago, a massive asteroid struck Earth. Not only did Jupiter not stop it, but it most likely caused the impact itself. One of the greatest existential threats to life on Earth is a tremendous cosmic impact. Whether from an asteroid, comet, or even an interstellar interloper, an energetic enough collision with Earth, typical of objects a few kilometers or larger in size, could easily cause a mass extinction event. In the worst-case scenario, it could even completely sterilize a living world, bringing an end to a multi-billion-year chain of life. These events have, very likely, happened all across the universe and even our solar system for many billions of years. Most famously, 65 million years ago, a large asteroid impacted Earth, causing the fifth great mass extinction since the Cambrian explosion, and wiping out 70% of all terrestrial species, including all of the non-avian dinosaurs.